Hello there. This lecture is all about discrete probability distributions. So just like the last lecture where you're still trying to determine how likely is any given outcome, only now instead of doing manual calculations, you're going to be using tables to figure out these values. So again, and organizations in today's business world face a great deal of uncertainty when they're making decisions. And probability is a really valuable tool for quantifying this uncertainty so managers can make more informed decisions. And remember, probability, which is symbolized as P, is just a fancy word for likelihood and is used quite a bit in business situations to predict how likely any given event is. Just like empirical probability that you've learned about before, the estimated probabilities for your sample are only as good as the information you have about the population. Remember, you always want to base probabilities on a large number of representative observations to make sure that the probabilities that you are basing or the data that you're basing your probabilities on matches the data that you're trying to extrapolate it to or the events that you're trying to relate it to. So probability can also be used to test the accuracy of claims about the population using a sample. So for example, if the manufacturer claims that only 1% of parts produced by their machine are defective, you could test this claim taking a sample of parts from the machine. And if the sample has a number of defective parts that is highly unlikely if the machine only has a 1% error rate, and it is likely that the sample should have had less defective parts if the error rate is 1%, well, then you could question the claims made by the manufacturer. So you can test the claims made by somebody who's selling you something using a sample of those products to see if their claim is accurate. Now, discrete probability distributions can be used to determine the probability of events in a sample when you know or think you know the probability of events in the population or the average number of events in the population. So for these types of probabilities that you're going to be calculating in this lecture, you do not need access to the raw data, and you aren't going to see a whole lot of formulas in this lecture. So I want you, again, to attempt all the gold problems without being tempted to look at the answers in this lecture, but I did include the answers in this lecture. So don't skip ahead and look. When you see a gold problem, pause the video and give it a try. And also be prepared to take notes. Okay, so the topics for today. I'm just going to give you a couple of terminology based on probabilities so that you can understand the language that I'll be using in this lecture. Then I will show you some of the binomial distribution notation, some of the terminology associated specifically with the binomial distribution, and then how to calculate the mean and standard deviation of the binomial distribution. Then I'll show you how to use the binomial distribution table to identify specific probabilities associated with events. And then I'm going to introduce you to the Poisson, not Poisson, Poisson distribution, and the notation for that, the terminology for that distribution, and how to calculate the mean and standard deviation. And then we'll do quite a few examples looking at the Poisson distribution table to figure out probabilities associated with specific events. Okay, so just some general probability terms. So a random variable, which is notated as x, this is the random value that occurs for a given selection or a given trial or the event of interest, really, is what x is. So with discrete random variables, those values are restricted to whole countable numbers. So for the discrete probability distributions that you're going to look at in this lecture, all the outcomes are fixed to whole countable numbers. So you can think about it as like how many, like the number of customers, the number of accounts, the number of purchases, the number of defects, those sorts of things. You can't split customers into fractions, right? You can't split number of defects into fractions. It's fixed whole number types of information. So we will use the binomial and the Poisson distribution for these types of discrete variables. Now there's also continuous random variables. So those are the kind of variables that are not limited to a fixed set of separate indivisible categories and have an infinite number of possible values that fall between two observed values. So this is something that's measured, not necessarily counted, and you can think about continuous variables as how much instead of how many. So you can think about money, time, or weight. All of those things can have fractional values, right? You can have $1.50. It's not just fixed to $1. You can weigh 105.6 pounds, right? It's not fixed to whole number responses. So the number of possible values is only limited by the precision of measurement when you have a continuous variable. So you may ask somebody what their age is in years, and it appears discrete, but it's not. So if somebody said 30, maybe they're exactly 30 years old, or maybe they're 30 years old, 2 months, 1 week, 1 day, and 22 seconds old. So there's fractional values. So for continuous probability distributions, that won't be in this lecture, but you'll see in the future that we'll use the empirical rule based on the unit normal table and figure out the probabilities for continuous variables. And then finally, the probability distribution is just comprised of all of the probabilities for all of the random variables in your outcomes. So the y-axis represents the probabilities, so the vertical axis, and then the horizontal x-axis just represents all the values for your random variables. And then that distribution can either be a graph or a table, and it's just a depiction of the probabilities of each event in the sample space. And I'll demonstrate how to create one of those. So now let's move on to the binomial distribution and when you want to use it. So the binomial distribution is appropriate when you have a fixed number of trials, when you have a specific sample size or a specific, remember lowercase n stands for sample size. And each trial only has two possible outcomes. Two possible outcomes or two possible events of interest. And the event of interest, the outcome that you're actually interested in predicting, is called a success, and that is what we label as X. So X stands for the number of successes or events of interest. And then if it's not an event of interest, then it's not a success, we call it a failure. Keep in mind, though, that just because you call something a success does not mean that it's a desirable event. It is just simply the event that you want to predict the probability of. So don't hear the word success and think it's something positive. It's just what you're interested in. So a couple of examples of situations where you'd want to use the binomial distribution because there's only two possible outcomes and it's a discrete type of event. So maybe you want to predict the probability that somebody signs a contract or the probability that someone does not sign a contract. Either they sign it or they don't, right? So if you're interested in the probability that someone does not sign a contract, then not signing the contract would be the success in this case. So not signing the contract is probably not a positive thing, right? It's not what you are happy about. But if that's what you're trying to predict, that would be called a success. You could also look at the probability of something being defective or fully functional. If you're looking at defects, it's either going to be defective or fully functional. There's only limited to two possible outcomes. It's a discrete event. You could look at the probability of being late or on time, or the probability of having the correct or the incorrect answer. All of those situations would lend itself to using the binomial distribution. Another condition for using the binomial distribution is that you have to have independent observations or trials. So you can't have conditional outcomes. So, for instance, the probability of the first customer signing the contract has no impact on the probability of the second customer signing the contract. Or if you're just randomly guessing, the probability of getting the first answer correct has no impact on the probability of getting the second answer correct. So independent, non-conditional observations. And then the third condition is that the probability of success and the probability of failure are consistent throughout the experiment. And this really gets at sampling with replacement. So remember, you remove one item from the population, put it back in before you remove the next. Now this really isn't typical in this type of study when you have this kind of data. But luckily this is not a necessary condition if the sample of observation is less than 5% of the population size. So when you have a really small sample size, replacement isn't that important because the probability with each selection isn't really going to change a whole lot even if you're not doing replacement. So for instance, if you are taking a sample of 10 out of 10,000, so the probability of the first selection would be 1 out of 10,000. And then the next one would be 1 out of, what would it be, 9,999. And the next one would be 1 out of 9,998. And you do that 10 times, and those probabilities are not much different at all. But if you have a situation where you're taking a rather large sample, compared to the population, then the probabilities are going to change quite a bit with each selection. So if you're only taking a sample of 2 out of a population of 10, well, the probability of the first selection would be 1 out of 10. And then if you don't do replacement, the probability of the next selection would be 1 out of 9. Those are drastically different probabilities. So all you really need to know for our purposes is that we aren't going to assume sampling with replacement, but that's okay because typically the population is very large compared to the sample, so we have a consistent enough probability throughout the experiment. I'm never going to throw something at you that may or may not be binomial, and the reason it's not is because there's not replacement. So don't get too hung up on that. Okay, so some terminology here and some notation. So E with the parentheses X, you'll see that right here. That stands for the mean. And in this case, the mean equals the expected number of successes based on the number of trials. And the way that you calculate the expected number of successes is you take the sample size, n, or the number of observations, and you multiply that by the probability of success, which is notated as p. So the probability of success, this p-value, is often a known value and will be given to you in the problems that you'll see in this class. Now q is the notation for the probability of failure. And the probability of failure equals 1 minus p. So remember the complement rule. So the probability of failure is the probability of any outcome, 1, minus the probability of success, p. And that's the probability of failure. Then the expected number of failures, or you could think about it as the mean for failures instead of the mean for successes, is just n times q. Or if you want to use this formula within this, n times 1 minus p. We just replace q here with the formula for q. And that is the sample size, or the number of observations, multiplied by the probability of failure, and that'll tell you the expected number of failures. Then the standard deviation. The standard deviation just tells you the variation or the differences that you would expect to see in the number of successes based on the number of trials. And the way that you calculate that, which is again just kind of the spread in the expected number of successes, is you take n multiplied, so the sample size or number of observations multiplied by the probability of success and multiplied by the probability of failure. And keep in mind, this would be the spread in the expected number of successes or failures. It's just whatever. Remember, like when standard deviation, back in the day, it was like the spread of scores relative to the mean. Well, now this is the spread of expected number of successes or failures relative to whatever you're looking at, the number of successes or the number of failures. Now you see this binomial formula here, and it looks kind of unwieldy, but that's okay. We're not actually going to be using the binomial formula because, again, we're going to be finding all these things in tables, and the tables are relatively accurate. They're accurate enough so that I'm not going to expose you to the formula. If you want to figure out how to use the formula, it is in the textbook, and I'm sure you can find lectures about it online. But the binomial formula just gives you the exact probability of an event of interest or a success in a given sample size based on the overall assumed probability of the event in the population. But again, we're going to use the tables, so you don't have to worry about this. So let's do some examples with the mean and standard deviation calculations. So if you know that the manufacturer of tanning beds claims that there's a 20% chance that a new bed will need to have at least one light replaced after 100 hours of tanning. And let's say that you just purchased 5 of these tanning beds. Well, how many tanning beds would you expect to need a bulb replaced after 100 hours? So in other words, I'm asking you for the mean here. So to figure that out, the mean, this is the formula or the notation for the mean, you take the sample size, 5 tanning beds, multiplied by the probability that one would need a bulb replaced after 100 hours. 20% just becomes 0.20, and you get 1. So you would expect that one of these tanning beds would need a light bulb replaced after 100 hours of tanning. Now, conversely, what's the expected number of tanning beds not needing a bulb replaced after 100 hours? Now, we're going to keep calling a success tanning beds needing a bulb replaced. So we're going to find now the probability of failure, or the expected number of failures here, right? This is the expected number of successes needing a bulb replaced. Remember, success isn't always a positive thing, it's just what we're interested in. Now to figure out the number of failures that we expect, we have our sample size of 5 tanning beds, multiplied by the complement rule, right? Because here we know that the probability of a success is 0.20, so the probability of failure is 1 minus 0.20, or Q, right? So this becomes 5 times 0.80, 1 minus 0.20, and you get 4. So you're expecting that 4 tanning beds will not need a bulb replaced. And guess what? 4 plus 1 equals your sample size of 5 beds. Because if we expect that 1 is going to need a bulb replaced, then we also expect that 4 will not. Now remember, we don't always think that 100% accuracy with this number, right? We know for a fact that after 100 hours of tanning, at least or only 1 bed is going to need replaced. To figure out the variation or the spread in that prediction, we figure out the standard deviation. So you take the sample size, which is 5 tanning beds, multiplied by the probability of success, or the probability that a bulb will need to be replaced, 0.20, and multiply it by the probability of a failure, 1 minus 0.20, or Q. So you just do that math, and then you take the square root of that. Don't forget to do your square root once you find your answers. And then the square root of 0.80 is 0.894. So this tells you the spread around the number of successes, for example. So what is the expected spread in the number of tanning beds needing a bulb replaced after 100 hours? So we would expect that 1 plus or minus, 1 being our mean, plus or minus our standard deviation, or, so 1 plus or minus 0.894 becomes, well, 1 minus 0.894 is 0.106. 2, 1 plus 0.894. So between 0.106 and 1.894 beds needing a bulb replaced. And because this is a discrete variable, I typically, once I get my actual values, I'll kind of round it and say, okay, this is pretty much what we expect. So 0.106 will be rounded to a 0, 1.894 will be rounded to a 2. So in reality, we're expecting either none or up to 2 tanning beds needing a bulb replaced after 100 hours of tanning. Not exactly 1, there's going to be some variation in this. So now I want you to try this example. Pause the video, see if you can find the expected number of successes. We're going to call the tanning bed needing the glass replaced a success, the expected number of failures, and then the standard deviation around the failures and successes. So pause the video and give it a try. All right. So hopefully you came up with something close to this, but if not, that's okay. This is the first time you've ever been exposed to this kind of stuff, so don't beat yourself up too much. But do beat yourself up if you did not pause the video and try it, because that's not okay. All right. So now again, the beds needing the glass replaced after 500 guests is considered a success. And so the expected number of tanning beds needing the glass replaced, you take the sample size, 5, multiplied by the probability that the glass would need replaced, 0.10, and you get 0.5. So essentially we are expecting less than 1 tanning bed needing the glass replaced. Now what's the expected number of failures in this case, or the tanning bed not needing the glass replaced after 500 guests? So you take the sample size, 5, multiply it by the complement rule of successes, because now we're looking at failures. So 1, the probability of it needing a bulb or needing the glass replaced or not, minus the probability of it needing it replaced. You get 0.90 would be the probability of not needing the glass replaced. So 5 times 0.90 is 4.5. Or, if you round it to a whole number to interpret it, probably all 5 of them. So you're probably not going to need to replace any glass after 500 guests. But what's the expected spread in these predicted values, these predicted number of tanning beds? Well, you find the standard deviation. So you take the sample size of 5, multiply by the probability that you will need to replace the glass after 500 guests, multiply by the probability that you will not. You end up with 0.045, take the square root of that, and your standard deviation is 0.212. So to figure out the expected spread in number of tanning beds, you would say, between 0.288 to 0.712. And the way I got that was I took my expected number of successes, my mean up here, subtracted my standard deviation, and then took it and added my standard deviation to get that range of values here. And if I round these to whole numbers to make it more interpretable, 0.288 would be rounded down to 0, 0.712 would be rounded up to 1, and we would say, between 0 and 1 tanning beds would probably need the glass replaced after 500 guests. So this isn't pinpoint accuracy, but it's better than nothing. It's a nice way to try to predict what you can expect in the future. So now let's shift focus to using the binomial distribution table. So let me go ahead and show you a picture of the table. All right, let's bring this table up here. So I tried to jot little notes for you guys, but they didn't come through very clearly, but that's okay. There it is. So if I break this table down for you, you have your x values here, you have your sample sizes here, and then you have these p-values here. So the n represents the sample size. So when you're using this table, the first thing you're going to look for is the sample size that you're using. And then you're going to look for, once you get to that, the probability of a success in the population. So those are these values here, these p-values. Then you're going to look for the probability of successes that you're trying to predict. But you need, and that's these x values. But you need to be careful because all of these numbers represent cumulative probabilities. And remember, cumulative probabilities tells you the probability of x less than or equal to whatever x value you're looking at. So for example, let's say I had a sample size of 2 and I thought that the probability of success in the population would be 0.01. This table tells me that the probability of 0 or fewer, so just 0, successes would be 0.9801. The probability of 1 or fewer, or in other words, 1 or 0 successes is 0.9999, and the probability of 2 or fewer successes would be 1. Think about that. Of course, it's a certainty if you have a sample of 2 that you're going to have 2 or fewer successes because the only thing you could have is 2, 1, or 0 successes. So that's why that's 1. So don't look at this table and say, oh, well, the probability of 2 successes in a sample of 2 is 1. No, the probability of 2 or fewer successes is 1. So much of this lecture is going to be dedicated to helping you figure out how to calculate the probabilities that you're actually interested in based on the values in the table. Because it's quite simple to say, I know my sample size, I know my probability in the population, oh, I'm interested in 1 success. You can't just do that. You have to really think about what these numbers represent to identify the values that you're actually looking for. So now that you've seen the table, you can look at this slide and it makes a little bit more sense. So the cumulative probabilities are those values in the body of the table. So the cumulative probabilities of successes. The n represents the sample size, the number of trials, the number of observations that you're working with. P is the assumed probability of the event of interest or successes in the population. X represents the number of expected events of interest or successes in the sample. Now again, these are cumulative probabilities. So if you want to know the probability of 2 or fewer successes, you could literally just go to 2 and find that probability. But if you want to find the probability of something or more successes, you would use the complement rule. So you would find the cumulative probability for the value just below the value, the number of successes you're interested in, and then you would take 1 minus that from the table, and you would get the probability of X or more successes. Another common problem that you would have, if you want to find the probability of an exact value, an exact number of successes, so not 2 or fewer, but 2 exactly, you would find the cumulative probability for the value of interest, the number of successes, and then you would subtract the cumulative probability for the value, number of successes just below it, and that would give you the probability of a specific number of successes. I'm going to show you tons of examples to make this a little bit easier, but once you look at the examples, it makes more sense. You can go back and review this, and hopefully it's helpful. Okay. So here's an example, and this is, I'm going to create the frequency distribution table. So the probability for every single possible number of tanning beds that needs a bulb replaced after 100 hours of tanning. So you've seen this before. There's a 20% chance that at least one light will go dark after 100 hours of tanning. So 0.20 would be my probability in my population, and I encourage you to use the tables that are posted in the modules tab and follow along with me here. So we also know we have a sample size of 5. So that's really the first place you start. You look for n equals 5 in the table. Then you look for p equals 0.20. And then you can start using these cumulative probabilities to find the values you're interested in. And here's my little hint about how to find the probability of a specific x value. So the probability of 0 beds needing a bulb replaced after 100 hours would be straight out of the table, because the probability of 0 or fewer, you can't have fewer than 0, so it would be 0.3277. But for 1, you can't just go to 1 and say, oh, 0.7373. Look at 1, p equals 0.20 with an n of 5. You can't do that. What you need to do is you need to take the probability of 1 or fewer, which is 0.7373, and subtract the probability of 0. So this represents the probability of 0 or 1. Then you subtract the probability of 0, and you're left with the probability of 1. And you'll see that right here in this table. Same principle for 2 tanning beds needing a bulb replaced. So this represents the probability of 2, 1, or 0. So you take that probability and you subtract the probability of 1 or 0, which is 0.7373. You see I did that here. So the probability of 2 or fewer minus the probability of 1 or fewer, and you're left with the probability of 2 exactly. You see the same pattern for 3, 4, and 5. So for 3, here's my 3. Here's what I'm looking at. This is the probability of 3 or fewer needing a bulb replaced, 0.9933. Not to be confused with the probability of exactly 3, right? So you take this probability of 3 or fewer, subtract the probability of 2 or fewer, and you're left with 0.0512. Then for number 4, 4 tanning beds needing a bulb replaced. Here's the probability of 4 or fewer, subtract the probability of 3 or fewer, and you're left with 0.0064. Then for 5 needing a bulb replaced, don't look at this and say, oh, absolutely, right? It's certain. The probability is 1. It's going to need a bulb replaced. 5 are going to need a bulb replaced. That's not the case. You need to say, all right, the probability of 5 or fewer, 1, minus the probability of 4 or fewer. 1 minus 0.9997, you get 0.0003. And if you're doing one of these tables, a good way to check your work is to add your final probabilities for each and make sure that they add up to 1, because it is an absolute certainty that out of 5 tanning beds, either 0, 1, 2, 3, 4, or 5 will need a bulb replaced. That is a certainty. Just like here, it is certain that 5 or fewer tanning beds are going to need a bulb replaced in a sample of 5. That's why this is 1, but that represents 5 or fewer, not 5 exactly. So be careful. Something else that I want to mention is that you should not round the values that you find in the table. So when you're recording your answers for table values, write the whole entire thing. Do not round. And another thing that I want to point out, remember the mean for this distribution, or the expected number of tanning beds needing a bulb replaced, was 1 when we calculated it before. And it's really no surprise that the probability associated with the expected value is the highest overall, right? So out of all of these, there's the highest probability that 1 tanning bed will need a bulb replaced, and that just confirms our expected value, or our mean that we calculated earlier. So to convert this into a frequency distribution graph, notice I'm using a histogram because this would be ratio data, true 0 point, and it's a numerical variable. All right, so just like you've done before, you've got your x values here, all the different values for your variable of interest, all the different number of successes, plot those along your x-axis. Then you just draw your bars to match the height of the probabilities that are listed along the y-axis. So we have a probability of 0.3277 of 0 tanning beds. So 0, probability 0.3277 on the y-axis. Now one thing that I want to mention about displaying your probability frequency distribution graph is that you want to use 0 to 1 on the y-axis. This will avoid an overrepresentation of probabilities, because if your axis simply went from 0 to the highest value, or 0 to 0.4096, then it would look like it's almost certain that you would have 1 tanning bed that needs a bulb replaced. But that's not the case, right? So if someone wasn't carefully reading the graph, they would see a bar that almost, was as tall as it could possibly be for one, and they may think that, oh, wow, the probability is really high. But it's still less than a 50% chance that that's going to happen. So be careful when you construct your graphs so that you aren't misleading with your information. So now let's do another example. You're going to see tons of examples in this lecture. So let's say that our competitor bought tanning beds from the same company, but they bought 11 tanning beds. And they want to know the probability that 2 beds will need a bulb replaced after 100 hours. So our sample size is 11 tanning beds, so you'd find n equals 11 in the binomial distribution table. The probability of a success or a bulb needing replaced in the population is 0.20, so you'd find p equals 0.20. And now we want to figure out the probability that x will equal 2, or that we'll need 2 beds with the bulb needing replaced after 100 hours. So I tried to color code things and sketch it out to make it easier for you. So here, what we're really looking at, remember, all these values tell us cumulative probabilities. So we can't just say, oh, there's 2, there it is, right? This tells us the probability of 2 or fewer. So I like to kind of map these things out. So I know that I need to find the probability of just 2, and I know that the only values I have in my table are x or fewer. So I can take the probability of x less than or equal to 2, which is what's actually here for 2, right? So the probability of 2, 1, or 0. So green represents that, so all of this, minus what I don't want out of this, right? The probability of x less than or equal to 1, or this. So I take my 0.6174, the probability of 2, 1, or 0, minus 0.3221, the probability of 1 or 0, and I'm left with 0.2953, which would be the probability of getting 2 tanning beds that need a bulb replaced after 100 hours out of this batch of 11. Or a 29.53% chance that 2 of these beds are going to need a bulb replaced after 100 hours. Here's another example. Same type of scenario. What's the probability that fewer than 3 beds would need a bulb replaced after 100 hours? Well, my sample size is still 11. The probability in the population is still 0.20. But now I want to figure out the probability that less than 3 will be selected. So if I kind of like map out my different number of successes, less than 3 would include 2 or 1 or 0 successes. So if I'm looking at this, I can say, all right, well, less than 3 is the same as saying 2 or fewer. And I can go straight to the table and find 2 or fewer right there, right? Because less than 3 would be 2, 1, or 0. This represents the probability of 2 or less, or 2, 1, or 0. So you just go straight to the probability for associated with 2 in the table, and you get 0.6174. Again, these all say x or fewer, probability of x or fewer successes. Less than 3 or fewer than 3 is the same as saying 2 or fewer, so you can just go right to that in the table. What's the probability that 5 or fewer beds would need a bulb replaced after 100 hours? So the last example was fewer than 3, so we just went to 2 or fewer, right? That's what this is. Well, this one is 5 or fewer. So this is asking about a cumulative probability. So finally, we can just go straight to 5 here. The probability of 5, 4, 3, 2, 1, or 0 beds needing a bulb replaced would be 0.9883. And that's our answer, right there out of the table. Yet another example. What is the probability that more than 5 beds would need a bulb replaced after 100 hours? And I've been kind of neglecting my zeros in this little sketch, so sorry about that, but oh well. All right, so our sample size is still 11. The probability of a success in the population is still 0.20. And now we want to figure out the probability that more than 5 beds would need a bulb replaced. So we're really looking at the probability of 6, 7, 8, 9, 10, or 11 needing replaced. So here we can use the complement rule. We can take the probability of any event and then subtract from what we don't want, right? 5 or fewer. So we can take 1 and then subtract 5 or fewer, 0.9883, and you're left with 0.0117. And you can see this one is here as well, right? The probability of 10, or 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, or 0 beds needing a bulb replaced in this sample of 11 is 1. 1 minus what we don't want here, right? Because we want it to be more than 5. So 5 or less, subtract that, and you're left with 0.0117. Practice makes perfect on this. I know it seems tricky, but once you try it out, it won't be as bad. You just have to really kind of map out what you're looking for and realize what's in the table to get what you want. All right. Speaking of practice making perfect, I want you guys to pause this video, try this on your own, don't look at the next slide, and see what you come up with. See how comfortable you are using the binomial distribution table. All right. So here we go. We have, in this example, we have a sample of 10 patient bills, and we know that the hospital administrator has recently received a complaint or an audit report that 15% of patient bills contain an error, and that was not acceptable. So they spent some effort. They tried to improve the billing process, and now they think that things are better, and they're trying to tell people that now the error rate is only 0.05 or 5%. So this is a situation where you are trying to test a claim about the population using a sample. So we take a sample of 10 bills, and we want to see what do we think is going on with this supposed error rate in the population if out of those 10 bills we found 3 with errors. So assuming that the managers are correct and they've improved the error rate to 0.05, here's all the questions that we're asking. So our sample size is 10 in this case, and then the probability that we're testing about the population is 0.05. All right, now we're ready to look at the answers. So n is 10, probability is 0.05. So what's the probability they would find 3 or less errors in a sample of bills? Well, 3 or less, that's a cumulative probability, so you just go straight to the table. So we've got our n of 10, probability of 0.05 in the population, 3 or less, there's our 3, and our answer is 0.9990. All right. Probability that they would find less than 3 errors in a sample of bills. That's not the same as 3 or less, but that is the same as saying 2 or less, or 2 or fewer, right? Because less than 3 would be 2, 1, or 0. So you could go straight to 2 in this table because this tells you the probability of 2 or fewer, and it's 0.9885 right there. Next one, what's the probability that they would find 3 or more errors in a sample of bills? So 3 or more. So if I kind of map this out, we're looking for 3, 4, 5, 6, 7, 8, 9, or 10, right? 3 or more. And I could take the complement rule by saying, okay, the probability of 0 through 10 is 1, right? There it is. Minus what I don't want, so the probability of 2 or fewer. So 1 minus the probability of 2 or fewer would give me the probability of 3 or more. So 1 minus 0.9885 equals 0.0115. So if we're looking for 3 or more, then we want to get rid of 2 or fewer, right? So that's what we did here. We took 1, the probability of any outcome, minus the probability of 2 or fewer, and that leaves us with the probability of 3 or more. All right, the next one. What's the probability that they would need, or that they would find 3 errors in a sample of bills if the error rate was only 0.05, right? So in this sample of 10 bills, how likely would it be that we got this result, that we found 3 errors if the error rate is really only 0.05? So to find that exactly, right, we take the probability of 3 or fewer, subtract the probability of 2 or fewer, and we're left with the exact probability of 3. Which is pretty darn low. If we multiplied this by 100, it would be a 1.05% chance that if the error rate was actually only 0.05, then in this sample of 10 bills, we would have 3 errors. So that leads us to the last question. So what conclusion can you reach about the accuracy of the manager's claim based on finding 3 errors in the sample of 10 bills? So based on this, I would question their claim and say that the efforts to reduce the billing error rate has not been as successful as the hospital administrators had hoped, right? The error rate is probably actually greater than 0.05 because it's really unlikely that we would have 3 bills with errors, and it's far more likely that there should have been less than 3 errors in this sample, right? It's pretty likely that that should have been the case if the claim was true. In fact, the expected number of errors in a sample of 10 bills, if the error rate was 0.05, would be 10 times 0.05, right? N times P. Remember the mean? And 10 times 0.05 is 0.5. And that's less than 1. We found 3 errors. That's telling me something is up with that claim. It's not accurate. And in fact, if you wanted to take it a step further, if you found 3 errors, you would have to have a sample size of 60 bills with 3 errors in it, not 10, and that would actually support the claim that there is only a 5% error rate. So 3 out of 60, that's about a 5% error rate. But 3 out of 10, not so much, right? That's a 30% error rate. That's not okay. So that does not support the claim made by the hospital administrators. So not only is it important for you to be able to find these values in the table, but you also need to be able to use these values to test claims or to explain what these values actually tell you about what you're looking at. All right, so this should be a familiar problem. You've seen this on practice problems for the Introduction to Probability lecture. So remember, we were looking to see what's the probability of getting all 4 questions incorrect on a quiz if there's 4 multiple choice questions, each with 4 response options and only 1 correct answer. So before, we said we used the multiplication rule for independent events. And we said, okay, well, the probability of getting 1 incorrect, if 3 out of 4 are incorrect, would be 0.75. And if there's 4 questions, and we're wanting to see the probability of all 4 being incorrect, you would just take 0.75 to the 4th power and get 0.316. Well, you can also use the binomial distribution table for this because we have a situation where we have only 2 possible outcomes for a single trial, right? You either get it right or you get it wrong. So if we're looking at this, and it's a discrete variable, you can't get a 1.5 correct on 1. You just either get it correct or you don't. Okay, so if we want to find the probability of getting 4 incorrect, we could say, all right, sample size is 4 questions. The probability of getting 1 incorrect is 0.75. And then we could say, all right, the probability of getting 4 or fewer incorrect is 1. This is kind of like the complement rule, right? Of course, you're either going to get 4, 3, 2, 1, or 0 incorrect if there's 4 questions. So the probability of any outcome is 1, minus the probability of getting 3 or fewer correct, 0.6836. You come up with the exact same answer that you did using that formula. So just yet another way that you can use something like this. All right, this is similar to the one you saw on the practice problems as well, only now we're looking at the probability of getting all 4 of the questions correct. Well, the probability of getting 1 correct, 1 out of 4 are correct, 0.25, 0.25 to the 4th power, 0.004, or you could use this table. So we're still using a sample size of 4, but now the probability of getting 1 correct is 0.25. And so we say, all right, the probability of getting 4 or fewer incorrect is 1, minus the probability of getting 3 or fewer correct, 0.9961, and you end up with 0.004, same exact answer as before. Kind of neat. All right, now we're moving on to a different distribution, and I kind of phonetically spelled it out for you, the Poisson distribution, not Poisson, even though you may think it's poisonous after this, but I don't know, it's kind of fun to play with the tables. So we're moving on, and so the Poisson distribution is a little bit different. So in a binomial experiment, the value of the event, or the number of successes, was limited to the number of trials, limited to the sample size. By contrast, a Poisson experiment can have any number of outcomes. For example, the number of customers who visit Roberto's during the next hour could be 0, 1, 2, 3, any number, right? It's not limited to a fixed sample size. It could be any number. So the Poisson distribution is appropriate for situations where the total number of possible events, or total number of successes, is really just impossible to determine. So you only know the number of events of interest, not the lack of events of interests. For example, you know the number of cars that arrive at a toll booth over a specific period of time, but there's really no way to look at the number of cars that don't arrive at the toll booth, right? Now, the Poisson distribution is also appropriate for processes that extend over time, space, or units with countable events of interest or successes. And it also relies on having a constant probability of events of interest across equal segments of time, space, or units. So for example, if we know that the average number of customers visiting Roberto's per hour is 11, this average is expected to apply to every single 1 hour increment. So we're expecting an average. If our average is 11, we are thinking there's going to be about 11 customers every hour. Now, it's nearly impossible that every hour will have exactly 11 customers. And you can only be confident in your probability of success as long as the average was calculated from a large representative sample, not just during the busiest or the slowest times, for example. So you also need to have independent segments that do not influence events in previous or subsequent segments. So for example, if 6 customers walk into the store during the first hour of business, this would have no effect on the number of customers arriving in the second hour. So we just have independent events, essentially. So now some terminology and notation, and what is the mean in this case. So X still represents the number of successes, just like it did in the binomial distribution. And it's what we want to find the probability of. So for example, we want to find the probability of the number of customers walking in. X would represent the number of customers that we're interested in figuring out the probability of. T stands for segment. Usually the segment is time, so that's why T is used. But the segment can be blocks of time, areas of space, number of units, or volume that the number of successes was originally based on. So in the example I've been using about, the 11 customers per hour at Roberto's, 1 hour would be T in this example. So typically, we're interested in the probability of an event across multiple segments or subsegments different from what we originally found the mean based on. So maybe we're interested in looking at the number of customers in a day, not an hour, or the number of customers expected in 30 minutes. So you have to be kind of careful when you're thinking about these and make sure when you're doing your calculations that it's based on the time period that you're actually looking at, even if it's not the original time period that the mean was based on. And I'll get into that more here in a second. All right, so this little guy right here, this is lambda. That's what it's called. It's a Greek symbol lambda. And it represents the average number of successes per t, the original t that it was measured in. And remember, success can even be a bad event in this case as well. So lambda would be the 11 customers, and then t would be in an hour. So this represents the mean 11 per hour. T. So although this is a discrete distribution, the mean can be a decimal, especially if it's calculated from many, many t's. So 11 customers per hour is fine, but you could calculate 11.5 customers per hour, and you still use that number, even though we're working with discrete variables. So this lambda t is going to be something that you see in the Poisson distribution table. And it's really important because if you're interested in the probability of a success in a subsegment or multiple segments of the original t used to calculate the lambda, you have to convert your t to the new segment in the original metric, so in compatible units, and then you have to multiply that by your lambda. So the probability of x based on the number of segments and the average number of events of interest or successes per segment is equal to lambda t. Or you can think about it as lambda times the new t put into the original metric, but maybe a fraction or multiples of this original time segment. So this is a pretty difficult concept to grasp for a lot of students. So I want to really break it down right here. So for example, if you know that the average number of customers per hour is 11, right? So the expected number of customers per hour, so lambda would be 11, and lambda is always 11 in this case because that's the original mean that we're working with. T, in this case, if we're looking at per hour, would just be 1 hour. That's the original, metric that we used. So lambda t would be 10 times 1 and be 11. And eventually you'll see the table and you'll see that you would be finding lambda t in the table. All right, the next one, expected number of customers in a day. Well, now lambda t is a little bit different. So lambda is still 11, but now we're looking at 24 hours, right? Not just 1 hour, we're looking at 24 hours because that's how many hours are in a day. So you wouldn't say 1 because it's 1 day. You have to convert it into the original metric that was used to find the mean. So how many hours are in a day? 24. So 11 times 24, we would expect 264 customers in a day, based on knowing that there's 11 per hour. What about the expected number of customers in 30 minutes? Well, lambda is still 11, but now t would be 0.5 hours. How many hours are in 30 minutes? Half, right? Half an hour, 30 minutes. So 0.5 hours would be our new t. So if we expect 11 customers per hour, we expect 5.5 customers per half hour, or roughly 6 if we're going to round it up to a whole number. So stop this video, give it a pause, try to figure out what would lambda t be, what would the expected number of successes be for number of customers in a week and number of customers in 20 minutes. So give it a pause, try it out. It's really important that you know how to do this so that you can use the table that you're going to see here in just a little bit. All right, so now let's look at the answers for those lambda t's that hopefully you worked on. All right, so expected number of customers in a week. So the first thing you need to figure out is t. And to figure out t, remember we have to keep it in the original metric, which is hours. So how many hours are in a week? Well, there's 24 hours in a day, and there's 7 days in a week. So there's 24 times 7, 168 hours in a week, right? Keeping it in the original metric of hours. So if there is expected 11 customers per hour, then we expect 11 times 168, 1,848 customers in a week. All right, now we're going to do a subsegment where it's a little bit easier to do multiple segments of time, but doing a subsegment is a little more challenging. So to figure out the expected number of customers in 20 minutes, you first need to find t by asking yourself, how many hours are in 20 minutes? Or how many 20 minutes are in 60 minutes, right? Keeping it consistent in the metric. 60 minutes is the same as saying 1 hour. So 20 minutes out of 60 minutes, or 20 minutes out of an hour, gives you 0.333 hours in 20 minutes. So when you figure out lambda t, if there's 11 customers expected in an hour, then there's 11 times 0.33, or 3.663 customers expected in any given 20-minute period. And again, this is discrete data, so if you want to round it up, I want to see this answer, but if you want, for explaining purposes, you would say we expect around 4 customers each 20 minutes. So now let's look at the standard deviation for the Poisson distribution. So remember, just like before, where the expected number of successes isn't always going to be the exact number of successes, the same thing applies here. Lambda t does not always equal the exact number of successes for any given t. There's still going to be some sampling error involved. So the question is, how much sampling error do we expect in lambda t? The number, for example, of customers expected per hour. So to figure that out, you just take the square root of lambda t. And when you get that, that tells you the expected sampling error, the expected spread in the number of successes. And then when you find those range of expected successes, like I showed you earlier, you just take lambda t plus or minus 1 standard deviation, and that gives you the range of expected successes in the time period of interest. So for example, if 11 customers visit Roberto's per hour on average, what is the range in the number of customers expected during any given hour? Well, this would be the original 11, right? 11 customers per hour, because we're still looking at 1 hour, the original time. So you take the square root of this lambda t, 11, you get 3.317. So if that's the expected difference around 11 in number of customers, you take 11 minus this sampling error and 11 plus the sampling error, and that gives you your range. So during any given hour, we would expect between, if we round these for explanation purposes, 8 to 14 customers in any given hour. The next one, what's the range and number of customers expected during any given day? Well, remember, we figured out, to figure out lambda t, we had 11 times 24 hours in a day, gave us 264. Take the square root of that, we get 16.248. So we know that we expect plus or minus 264 plus or minus 16.248 customers in a day. So if we take 264 minus 16.248, we get 247.752. 264 plus 16.248, 280.248. Or if we round these to whole numbers, we expect between 248 and 280 customers on any given day. Now, what is the range in number of customers expected for any given 30 minutes or half hour? Well, we've done this before, the lambda t, right? If there's 11 customers expected in any hour, then there's 11 times 0.5 customers expected in any given 30 minutes or half hour. Take the square root of 11 times 0.5, which is 5.5. Take the square root of that, you get 2.345. So we expect 5.5 plus or minus 2.345 customers for any given 30-minute period. So if you take 5.5 and add 2.345, you get 7.845. Take 5.5, subtract 2.345, you get 3.155. Or you could say you expect, when you round these, between 3 and 8 customers for any given 30 minutes. So now I want you to pause this video and try to figure out the range and number of customers expected during any given week or any given 20 minutes. And the bulk of these calculations you've already done in the previous example. So pause this video and give it a try. All right. So what is the range and number of customers expected during any given week? So if you expect 11 in an hour, then you expect 11 times 168 in any given week, because there's 168 hours in a week. So you take the square root of that, square root of 1,848, you get 42.988. So you take that 1,848, subtract this, 42.988, add this, 42.988, and you say, between 1,805.012 to 1,890.988, or if we round it to whole numbers, we expect between 1,805 and 1,891 customers during any given week. All right, the next one. What is the range and number of customers expected for any given 20 minutes? So we already found that we would expect about 3.663 customers in any given 20 minutes. But when we want to figure out what would be the range, because that may not be wholly accurate, take the square root of that. That gives you the error you would expect. Add that to your mean or your expected value or your lambda t. Subtract it from your expected number or your lambda t. You get 3.633 plus or minus 1.914 gives you 1.719 to 5.547, or between 2 and 6 customers expected for any given 20-minute period. So if I just ask you how much error would you expect in your anticipated or your expected number of customers in this example, I would be asking you for this standard deviation. But if I wanted to know the range in expected values, you would need to take that standard deviation, subtract it from the mean, and then take that standard deviation and add it to the mean, and then round to whole numbers. So now I want to show you the Poisson distribution table. So let's bring it up now. Okay. So the Poisson distribution table includes lambda t. So that's the first thing that you want to find. And lambda t is presented in bold along the top row of each different set of tables here. And then x represents the number of successes. And again, these represent cumulative probabilities. So in like the Roberto's example, if our lambda t was, 1, then we would say, all right, well, there's a 0.3679 probability of getting 0 or fewer customers in an hour. There's a 0.7358 probability of getting 1 or fewer, so on and so forth, just like the binomial distribution. So now let's look at the more thorough explanation of this table. So the first thing, you're going to be locating cumulative probabilities of events of successes based on lambda t, which we already discussed. It's the average number of successes for a given subsegment or multiple segments of t, or just t, but really just the expected number of successes in your time frame that you're interested in. And then x, how many successes you are interested in. So this is, again, the same as the binomial distribution because those values are cumulative probabilities. The probability of x or fewer successes. And then this is just a rehashing of what you saw before to find the X or more, you use the complement rule to find X. You take the cumulative probability for the X that you're interested in, subtract the cumulative probability for the value right underneath it. So now let's do an example of constructing the frequency distribution table and then eventually the graph for the Poisson frequency distribution. So based on data collection over the past year, we know that 11 customers visit Roberto's per hour on average. And the probability of X customers arriving in we want to know the probability of however many customers arriving in any 5-minute period. So that would represent all these different X values. We want to figure out the probabilities with all of these. So the first thing you need to ask yourself, what is T? How many hours, the original time period used to calculate the average, are in 5 minutes? So to figure this out, you could take 5 minutes divided by 60 minutes, the number of minutes in an hour, and you get 0.083. So that is our T. So then we can use that T to figure out lambda T. So we have 11 times T, 11 per hour times the number of hours in 5 minutes, 0.083, repeating, and you get 0.916 or 0.90-ish, right? Because you won't find 0.916 in the table under lambda T, but the closest thing to it is 0.90. So that's where you're going to be looking in the table. So just like before, we are not going to say, oh, for 7 customers, we just go right to 7, and that's our answer. This tells you the probability of 7 or fewer customers in 5 minutes. So you need to be careful. All right, and I'll walk you through this just so that you really understand it. All right, so the probability of 0 customers in the next 5 minutes would be right here, right? 0.90 is our lambda T-ish. And this is the probability of 0 or fewer. You can't have fewer than 0, so this is essentially the probability of 0, 0.4066. Moving on to the probability of 1 customer in the next 5 minutes. So this is the probability, 0.7725, of 1 or fewer customers. Subtract the probability of 0 customers, and you end up with 0.3659 for the probability that 1 customer will walk in. Then the next one, if we're wanting to figure out the probability of 2, you say, all right, 0.9371 is the probability of 2 or fewer minus the probability, 0.7725, of 1 or fewer, and you are stuck with 0.1646 for the probability of 2 customers coming in. So you see that process all the way throughout all of these, all the way down to if we're looking at the probability of 7 customers. So the probability of 7 or fewer is 1. The probability of 6 or fewer is 1. 1 minus 1 is 0. And just like before, you can test your accuracy by adding all your probabilities up in your table, and you should get something that looks like a 1, right? Because just like before, the sum of the probabilities equals 1, or in other words, there's a 100% chance that you will have 0, 1, 2, 3, 4, 5, 6, or 7 customers in the next 5 minutes. Or is it? This is a little different, right? Because you don't have a fixed sample size. Maybe something crazy happens. Maybe all of a sudden you get very busy and in the next 5 minutes you get 30 customers. Who knows, right? The accuracy of this stuff is really dictated by the quality of your data collection. So of course you could have a situation where you have more than 7 customers show up, or 7 exactly. But it's very, 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 very unlikely if your data collection was accurate in the first place. And to me, collecting data over a year is a pretty good time period because that includes, busy seasons and slow seasons and all times of the day. So I would be pretty confident that we are not going to see 7 customers or more than 7 customers enter Roberto's in the next 5 minutes based on this data. All right, so we take those probabilities associated with each value, each possible value here, or each expected value that you could have, number of successes, and then we just construct the frequency distribution graph. So all these x values represent the number of successes, probabilities are along the y-axis, and again, I created the y-axis so that it's ranged from 0 to 1, just to represent the fact that up here would be the only certain outcome, right? An outcome of 1, and none of these are certain. You wouldn't want to list this from 0 to 0.4066 because then it would over depict how probable all of these different number of successes are if somebody wasn't really paying attention to the table. And just like before, remember that the highest probability was associated with the average that we found? Well, in this case, our lambda t is 0.90, and the highest probability is 0, and this is below 1. And then the next highest probability is for 1. And so you can kind of see that that happens here too, right? It's more likely that we're going to get 0 than 1. This is less than 1. But it's also, similarly likely that we're going to have 1. So it's kind of, looking at the lambda t here, you can see that it's pretty close. And if we actually had 0.916 in the table, I bet you that 1 would be more probable. There's just a little bit of error going on here because we didn't have 0.916 in the table. So that is one disadvantage of using the table instead of a formula. So there is a Poisson formula. I didn't include it, but you could use it. But I didn't include it. We're not going to use it. These estimates are good enough because there's error associated with probability anyway. It's not 100% accuracy. So let's do another example using the Poisson distribution table. So let's say that a customer support center for a computer manufacturer receives an average of 1.5 phone calls every 5 minutes. So what is the probability that no calls will arrive in the next 5 minutes? So in this case, lambda t is equal to the original average because we are using the same time period that the average was calculated on, right? So if there's 1.5 phone calls every 5 minutes on average, then in the next 5 minutes, we expect 1.5 phone calls. So that part is already done for you. You don't have to figure out subsegments or multiple segments at a time because it's still 5 minutes. And in this case, we want to know the probability of 0. So luckily, we can go straight to the table for that. So we find lambda t, 1.5, probability of 0 or fewer, can't have fewer than 0, so the probability of 0 or fewer is the same as the probability of 0, 0.2231. The next one, what is the probability that 3 or more calls will arrive during the next 5 minutes? So we're looking for the probability of 3, 4, 5, 6, 7, 8, or 9. Again, I didn't include the 0 in here. Sorry about that. So 3, 4, 5, 6, 7, 8, or 9. And what we need to do is take the probability of 0 through 9 and subtract the probability of 2 or fewer. So take the probability of any outcome, subtract the outcomes we aren't interested in, because if we want it to be 3 or more, we don't want to include the probability of 2 or fewer. So we have 1 minus probability of 2 or fewer, 0.8088, and we end up with 0.1912 is the probability that we will have 3 or more calls during the next 5 minutes. So now, what if we want to know the probability that 3 calls will arrive during the next 10 minutes? So be careful, right? Lambda t is no longer 1.5 because we are no longer looking at a time frame of 5 minutes, which was originally the time frame for the average or the mean calculation that we have, that 1.5. So how many 5 minutes are in 10 minutes? 2, right? 5 minutes times 2 gives you 10 minutes. So to find lambda t, you take 1.5 times 2. So if there's 1.5 phone calls on average every 5 minutes, then we expect 1.5 times 2, 3 phone calls on average every 10 minutes. So now when we go to our table, we're looking for a lambda t of 3. And I hope you have your table out and you're working with me through this. Okay, so to find the probability of exactly 3 calls, you need to take the probability of 3 or fewer, which is 0.6472, and subtract the probability of 2 or fewer calls. And then you end up with 0.6472 minus 0.4232. 0.224 is the probability that you would see 3 calls during the next 10 minutes. What is the probability that no more than 2 calls will arrive in the next 10 minutes? This is the same as saying if it's no more than 2, then it's 2 or fewer. So be careful untangling the verbiage in some of these questions. You have to really think about what it's asking you. So what is the probability that no more than 2, or in other words, 2 or fewer calls will arrive in the next 10 minutes? Well, I love these kinds of questions because I can go straight to my table. Because 2 or fewer, if I go to 2, this is the probability of 2 or fewer, right? It's a cumulative probability. And I'm looking at lambda t of 3 because I'm still looking at a 10-minute period, and I already figured out there's going to be 3 calls expected in 10 minutes if there's 1.5 calls expected in 5 minutes. So right there's our answer, 2 or fewer, or in other words, no more than 2 calls, probability 0.4232. So now I want you to pause this video and attempt these problems using the Poisson distribution table and the examples that I just showed you. All right, now let's look at the answers. So if the mean number of errors per page made by a member of the word processing pool for a large company is 1.5 errors per page, right? Errors per page. Then with the number of errors distributed according to Poisson distribution, so I just kind of threw that out there for you just so you know that's what you're working with. You want to know if 3 pages are examined, what is the probability that 3 or fewer errors will be observed? Well, if there's 1.5 errors per page, then we would expect 1.5 times 3 errors, or 4.5 errors, in a sample of 3 pages. So the lambda t that we're looking at is 4.5. So we look for lambda t, 4.5 right there. And then we want to know the probability of 3 or fewer. Well, that is a cumulative probability, right? The cumulative probability is x or fewer. So 3 or fewer is right there on the table, 0.3423. Well, what if we wanted to know the probability that more than 3 errors will be observed? Well, we could take the probability of 0 to 16 errors being observed, so the probability of any outcome in this example, and subtract what we don't want using the complement rule. So if we want to know more than 3, we could take 1 minus the probability of 3 or less, right? Because more than 3 would be 4, 5, 6, all the way up to the maximum probable outcome. So we have 1 minus less than or equal to 3 leaves us with more than 3. So 1 minus 0.3423 gives us a probability of 0.6577. Or we could say there's a 65.77% chance that in 3 pages you would find 3 errors if there's average of 1.5 errors per page. All right, now the last set of answers, or the second to last, really. So if the mean number of errors per page is 1.5 per page, and we want to know, if we look at 5 pages, what's the probability that 3 or fewer errors will be observed? Well, now we're looking at 5 pages, right? So if there's 1.5 per page, well, we take 1.5 times 5 to get 7.5 errors per 5 pages, and that's our lambda t, 7.5. And then we want to figure out the number, or the probability of 3 or fewer errors. Well, this is a cumulative probability, 3 or fewer. So we just go right over to 3 and we find 0.0591 and we are done with that one. If 5 pages are examined, what's the probability that fewer than 3 errors will be found? Well, lambda t is still 7.5. 5 times 1.5, right? 5 pages times 1.5 average errors per page. And we're looking for less than 3. Well, saying less than 3 is the same as saying less than or equal to 2, right? Because if you have less than 3 errors, you can have 2, 1, or 0 errors. So you just go to the cumulative probability for 2, because remember that tells you the probability of 2 or fewer errors, or in other words, less than 3 errors, and you get 0.0203. All right, guys, that's it. That's all I have for you. I hope that all these examples helped you learn how to navigate these tables and feel more comfortable doing this on your own. If you have the textbook, you'll see the hypogeometric distribution is in there. I'm not going to cover that or make you responsible for it. It's only used when there is not sampling with replacement, or conditional sampling as it's called. But remember, even if we don't have replacement, we can still use the binomial distribution when the sample size is less than 5% of the distribution, which is typically the case. So I'm not going to cover that distribution. All right, have fun, play with these tables, get used to it, and get comfortable with figuring out probabilities.